So today we're looking at constructing root systems and automorphisms. So we know what all of the possible Dinkin diagrams of root systems, the possible connected Dinkin diagrams of irreducible root systems. But we need to actually make sure that they all belong to a root system. So I'll write down, do our Dinkin diagrams all correspond to root systems? And we'll also be looking at the automorphism group of the automorphisms of a root system. Alright. So we're just going to be doing all this, it looks like mostly by direct construction, which we will be also seeing at their Weil groups. So to start out, we're going to be looking at constructions. We will be working in, so we are in R to the n with orthonormal unit vectors epsilon I from 1 to n, which are our basis. The integer span of this basis is a lattice we're going to call I. So we will take E to be our Rn and phi not necessarily equal to, but based on the vectors in I of given lengths. Let me see that, which will make our root system phi finite pretty trivially. Finite and spanning E. So we have R1, so we have our first two actually conditions of our root system. And so we can verify this is a root system. They go through a more explicit proof of they're talking more specifically about all the axioms and how you satisfy them, but they do it in a very vague, abstract way, so I don't think you get much going through all what they've read here. So we will look at our individual cases now. And you can verify that these that we're setting up match the Cartan matrices for our given diagrams. So first off, AL, mind L is just, has to be at least 1. So let E be the L-dimensional subspace of R to the L plus 1 orthogonal to the sum of all of our basis elements. Let I prime be the intersection of I and E. And let phi be the set of alpha in I prime such that the form of alpha with itself is equal to 2. So that alpha, which is alternatively equal to the set of differences of basis vectors for distinct basis vectors. And this is a construction we've seen before. The vectors AI being equal to EI minus EI plus 1 are independent. I made a mistake there. And we can write each EI minus EJ as the sum of alpha n from I to j minus 1, as we've seen before. So they form a base of our phi, giving our Cartan matrix. And also we notice that reflection across alpha I by alpha I permutes the indices I and I plus 1 and leaves all others fixed. So sigma alpha I corresponds to the transposition of I and I plus 1 in the symmetric group of L plus 1. So we have trivially, because we should know from group theory that these transpositions generate the entire symmetric group. So the Weyl group is isomorphic to the symmetric group of L plus 1. Alright, now let's look at our B. Keep in mind, in this case, B has to be at least 2, otherwise it coincides with A. So we're going to let, in this case, E be R to the L. And phi is going to be the set of alpha and I of length 1 or 2. Giving us long and short vectors. So that our phi consists of the vectors to be length 1, it has to be plus or minus ei. And to be length 2, has to be plus or minus ei plus or minus ej for I not equal to j. This gives us L vectors E1 minus E2 up through e to the L minus 1 minus EL along with EL itself are independent. And generate all roots. Generate. I don't know if that's the right word in this context, but that's what I'm going with, all roots. So we can generate short roots, EI, as the sum of e to the n minus 1 minus e to the n from n equals let's rewrite this. Let's rewrite this whole thing. It's going to be e to the L plus the sum of e to the n minus e to the n plus 1 of n equals I through to L minus 1. So essentially we started with e to the I, which is going to give us an extra term e to the I minus 1. And we telescope that all the way out to be e to the I minus e to the L, and then we just add e to the L back in. And we can make long roots from our short roots in the trivial manner. Which gives our Cartan matrix. In this case, the file group acts as a group of both permutations and sign changes. And the sign changes that is not legible. Sign changes of our collection epsilon I from 1 to L. So the file group is isomorphic to I'll just write out in words, is isomorphic to the semi-direct product of L copies of the integers mod 2 corresponding to all the sign changes and our S to the L corresponding to the rotations. Our CL, L has to be at least 3, otherwise it corresponds with B. CL corresponds to the root system dual, which I think is a concept they introduced on a homework. I'll check into that later. Of BL, but it's easy to see how this works in the context of a Dinkin diagram. In E as R to the L, our root system is the set of all plus or minus 2 EI and our old EI plus or minus EJ for I not equal to J. With our base, in this case being epsilon 1 minus epsilon 2 up through epsilon L minus 1 minus epsilon L, and then 2 epsilon L. And with the same file group as in BL. Now for our last family corresponding to the forks is DL. L has to be at least 4, otherwise it's isomorphic to A once again. We're going to let E be equal to the real numbers to the L, and our root system is going to be alpha and I of length 2, which is going to be the set of plus or minus EI plus or minus JI, EJ for I not equal to J. We have a base of L vectors in the family of epsilon 1 minus epsilon 2 up through epsilon L minus 1 minus epsilon L, and then conjoined with epsilon L minus 1 plus epsilon L. So we can get epsilon L by subtracting the last one from the second last, and then we can go on from there. No, that's not, you know what I mean. Like, you can get any vector in that top space easily from this. And the file group corresponds to sign changes and one second, I gotta no, it corresponds to permutations as always, and even sign changes. So changing the sign of two or more of like an even number. So the vowel group is isomorphic to the semi-direct product of our list of signs except -1 degree and the symmetric group of size L. Next up is E8 with E6 and E7 being subsystems. Are subsystems of E8, so we can just construct E8 and crunch them down to get E6 and E7. So we're going to take E to be the 8-dimensional real vector space, and take I prime to be equal to I plus Z of E, the sum of E1 through epsilon 8 over 2. And then I double prime be the subgroup of I prime of elements of the form C over 2 of epsilon 1 summed through epsilon 8 plus the sum of some Ci epsilon I sorry. Oh. So plus EI all multiplied by coefficients, for which C plus the sum of our Ci is an even integer. We now define our root system to be the set of elements in I double prime of length 2 so our root system consists of the old familiar plus minus epsilon I plus minus epsilon j for I and j distinct, and the set of half of the sum of -1 to the k of I epsilon I, where the sum of our ki, where each k to the I is 0 or 1, and the sum of all ki is an even integer. All inner products are in the integers. Given that we have our I prime being a lattice bigger than I, you do have to check this. Take as a base 8 elements set of 1/2. The first element is 1/2 of epsilon 1 plus epsilon 8 minus every other epsilon. And then epsilon 1 plus epsilon 2. And then epsilon 2 minus epsilon 1 up through epsilon 7 minus epsilon 6. This has a file group of order 2 to the 14 times 3 to the 5 times 5 squared times 7. Have fun with that, I guess. I wonder what that number is. That's going to be something big, right? Let me just take a quick second. I need a break here on my hand anyways, so 14 times 3 to the 5 times 5 squared times 7. This is so the order of our file group is 6, 9, 6, 7, 2, 9, 600. So 696,729,600. So that's kind of the complexity we're dealing with there. Now F and G, as we saw before, have a unique Dynkin diagram of their size. So we just have one case to look at in these cases. So we're gonna take E, of course, to be R4. R prime to be I plus Z of epsilon 1, 3, sum of all our epsilons over 2, and a root system to be roots to be elements of I prime of size either 1 or 2. So we're going to have long and short roots, because keep in mind this does have a double connection as a Dynkin diagram. So our phi consists of plus or minus epsilon I, plus or minus epsilon I, plus or minus epsilon j for I and j distinct, and plus or minus 1/2 of, and I'll write it like this, 1/2 of plus or minus epsilon 1, plus or minus epsilon 2, plus or minus epsilon 3, plus or minus epsilon 4. With all of our diagonal or angle brackets, alpha and beta, being integral. Take as base the set of epsilon 2 minus epsilon 3, epsilon 3 minus epsilon 4, epsilon 4, and then epsilon 1 minus epsilon 2 minus epsilon 3 minus epsilon 4 over 2. With our Weil group being order of 1152. And finally, for G2, we have already constructed this root system explicitly, but just as a reminder, we're going to take E to be the subspace of R3 orthogonal to 2 epsilon 1 plus epsilon 2 plus epsilon 3, where I prime is the intersection of I and this E, and our root system is the collection of alpha in I prime such that the size of alpha is either 2 or 6. So that our root system phi is up to sine epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, epsilon 1 minus epsilon 3, 2 times epsilon 1 minus epsilon 2 minus epsilon 3, 2 times epsilon 2 minus epsilon 3 minus epsilon 1, and 2 times epsilon 3 minus epsilon 1 minus epsilon 2. As a base, I'm going to choose epsilon 1 minus epsilon 2, and minus 2 epsilon 1 plus epsilon 2 plus epsilon 3. And that will give us our G2, so now we know that all of these are actually Lie algebras. Which means we can kind of close this chapter on the theorem. It says that each Dynkin diagram of A to G has a corresponding irreducible root system. And this will bring us on to automorphisms of, yeah, okay, that's pretty short. To finish off this chapter, we're going to look at automorphisms. Of our root system. I'll put a side note here. I think that the Weil group of G2 is the dihedral group of order 12. Where the notation of the dihedral group is always kind of messy. So this is the one with order 12. Now, automorphisms of our phi. If you recall that the Weil group is a normal subgroup of the automorphism group of phi. So we're going to let gamma be the set of automorphisms of phi that preserve our base for a fixed base. Then obviously gamma is a subgroup of the automorphisms of phi. We see that if we have an element taf in both gamma and the vial group, then taf is clearly equal to 1. Also see for arbitrary taf in the automorphism group of phi taf of delta is a base of phi, so there exists sigma in the vial group such that sigma of taf of our base is just the original base. So taf is in be an element of gamma times an element of the vial group. Thus we see that the automorphism group of phi is the semi-direct product of gamma and the vial group. Okay. For all taf in our automorphism group, and alpha and beta being roots, we have that the angle bracket of alpha and beta is the angle bracket of taf of alpha and beta. So each taf in gamma determines an automorphism of the Dinkin diagram of phi with t being equal to 1 if it acts trivially, by delta spanning E and we see that we also see obviously each automorphism of the Dinkin diagram determines an automorphism of phi. Thus, our gamma may be identified with the group of diagram automorphisms. And so what are those? Well, there's a type, the type, positive roots, the order of W, the order of the Weyl group, structure of the Weyl group, and our gamma. Another table, so this is going to be real messy. Just the number of positive roots, of course. So for AL, we have L plus 1 choose 2 positive roots. L is the symmetric group of order L plus 1, so it has L plus 1 factorial elements. And as a diagram, keep in mind it's just a straight chain, so the only automorphism is to just flip it around, giving us 2 possible automorphisms, giving us an automorphism group of Z over 2Z. For BL and CL, keep in mind these are a straight chain ending with a double chain, so they're asymmetric. These have L squared positive roots. You have a structure of Z over 2Z to the L, semi-direct times S to the L. So they have 2 to the L times L factorial elements. And there's no non-trivial automorphisms of their diagrams. Now for delta 4, because keep in mind delta L is the branch. Normally there's only one automorphism, which is just mirroring it. But in the case of L4, every branch along the split has one component, so you get more symmetry in the case of L4. So in D4 you get, and as we're looking at D4, let's look at DL for L greater than 4. Number of positive roots doesn't change here, so this is going to be L squared minus L. This is going to give us 12 positive roots. You have 2 to the L minus 1 times L factorial. It's going to be 8, I believe, times 24. What is that? Oh, I don't feel like doing this in my head, but 8 times 24. 16, this would be 192, I believe. The structure is going to be Z over 2Z to the L minus 1. Semi-direct with SL, as always. So in this case, it's just going to be Z over 2Z cubed, semi-direct product with S4. And here's the big difference. When L is at least 4, we just have 2 automorphisms, with a non-trivial one being swapping the elements at the end of our chain. When L is 4, though, we can permute any, because it looks like this, right? I guess, let me draw these out. So this one we have like this. A1, right? You can just mirror it. B2 all looks like this, so there's no non-trivial symmetry there, right? For big D, for DL for big L, we can just swap this. But for D4, we have this full option of rotation, which gives us this S3 as our special group. Now there's even more. Now we have to consider our exceptional groups. We have E6. E6, keep in mind, is this one. So we have 36 positive roots. 2 to the 7 times 3 to the 4 times 5 elements. 3 to the 4 times 5 elements in our positive root system. Good luck. I'm not writing out the structure of W. And once again, we have just a reflection for our non-trivial diagram automorphism, and then for E7 and E8. In both these cases, we have an asymmetry. And so we're not going to have any diagram automorphisms that aren't trivial. We have 63 and then 120 positive roots. We have 2 to the 10, 3 to the 4, 5 times 7. I'll put 5 to the 1 just to make the notation easier. Elements in W here. As I said before, we have 2 to the 14, 3 to the 5, 5 squared, 7 elements in our Weyl group of A to the 8. And the Weyl groups are not going to be written down here because I'm not going to spend my life like that. And then we have F4 and G2. F4 and G2, if you can recall these, F4 is like this with a very asymmetry in the middle, and G2 is just the whole big mess. So neither of these are going to have any diagram automorphisms. F4 has 24 positive roots and 2 to the 7 times 3 squared elements in its Weyl group. And G2 has 6 positive roots. It has 2 squared times 3 elements in its Weyl group, which is D12 or D6, depending on how you write it. I'm just gonna, for this purpose of this diagram, I'm gonna write, it's like Z over 3Z. I believe it's the semi-direct product with Z over 2Z. You know what, that's confusing. I'll just write out, it's the dihedral diagram of order 12. And that's really all of our diagrams. So you can see which ones are going to have non-trivial automorphism groups beyond the Weyl groups. It's going to be A1, D5 nap, and then E6 are going to have a like extra dimension. They can have like one corresponding subgroup beyond the Weyl group. Well, you know what I mean. Like the Weyl group is going to be ordered 2 in them. You have the Weyl group and then the Weyl group with this reflection of the roots. And then D4 just kind of has its own crazy thing going on. So that's pretty cool. Next time we will be looking at weights. And then I think we'll be taking a break from this sort of talk. Maybe that might be the end of this talk of Cartan matrices and Dynkin diagrams in this book, which might make it the end of the talk of like it in this video series, at least for now. So I don't know. We'll see what happens there when it comes. But yeah, thanks for watching.